Alrighty then. So, right here's some heavy atoms stretching. And so right here we're seeing the carbon hydrogens. These are going to be the carbon hydrogen stretches. Depending on what they're attached to, they're going to show up somewhere between 2700 and 3300. For example,
Sorry, this is saying when it's attached to like a really heavy thing, like if it's the substituent.
yeah. So the heavy atom attached to the hydrogen. If both sides are about the same, you're going to see a huge frequency shift. But that's very rare because you'd only be able to do that with H2, right? Yeah, or like a lithium hydride or something. Yeah. So typically speaking, hydrogen's attached to something that's at least 4 or 5 times its weight, right? So that being a heavy atom compared to it. And so what ends up happening is it's like a door spring, okay? So you have like the door, the wall, right, that's attached to. The door wall is much heavier than the spring, right? And so what you see is it goes ding, and then it goes real rapid, right? Okay. On the other hand, if you have something like a just a normal spring of the same, have you ever played with those when they're not attached to anything? You go ding, and it doesn't go as fast, does it? Yeah, because the other end also moves, doesn't it? And uses up energy. Okay, so the NH stretch is going to appear 3,300 to 3,500. Note that's quite a bit higher than the CH. And the alcohol is going to be about 3,600. It's pretty consistent because you already have a lot of electronegativity difference between those two. So there's not a lot of other things that can happen to it. In these cases right here, depending on exactly what you have it attached to, that's going to change the force that's holding it with, which also changes the bond distance, by the way. And that's going to change your frequency that these will vibrate at. For example, when they're on an aromatic ring, what sort of frequency were you looking at? 3,100, right? Okay. If you had it off of, say, a carbonyl, this would change the frequency considerably, wouldn't it? Okay. All right, so if you look at an alkane, sp3, then the CH stretch is going to appear below the 3,000 wave number, typically somewhere in the 29-ish hundred region, like a 2940, that sort of thing. If you have an alkene, that's an sp2 character, you're going to see the CH stretch appear between 3,000 and 3,100 typically. And if you have an alkyne, then the CH stretch is going to appear up at 3,300-ish. Now, note again that SP character, that's the same trend that you'd seen for the acidity for these, right? And that's the exact same reason here, is you're actually changing the character of the bond. You're making it more and more S character, right? And so it's pulling in the electrons more and more for that. And so it's vibrating at higher and higher frequencies. Okay? And so all of these are related to each other. This is what you're looking at in terms of ball and spring model. So again, remember that we're looking at a heavy ball here with another heavy ball here. If we decrease the mass on one side of this, what's going to happen is you're going to see this vibrate much faster, right? Because it doesn't have to move as much weight. Okay. All right. And so as we decrease the mass, we're going to get faster and faster frequency of vibration, and so we're going to get larger wave numbers. So we have deuterium. Anybody remember deuterium? It's the isotope of hydrogen that has a mass of 2, right? So it has nearly identical chemical properties. It's still the same number of protons. It's still hydrogen. Still does the same chemistry for the most part. And we have a CH bond, therefore we can have a CD bond as well. These are going to have essentially the same bond strengths. They're going to have essentially the same bond distances, right? Because again, it has the same number of electrons, same number of protons, right? Only difference is the mass is twice the mass. So what would you expect to happen with the vibrational mode for this. Is it going to vibrate at a higher frequency or a lower frequency? So would you expect the CD to vibrate at a higher frequency or lower frequency?
Lower because it has more mass.
Exactly. Lower because it has more mass, right? For the same amount of energy, if we strike it, it's going to cause it to end up vibrating at a slower speed, right? Just like if you were to take a pendulum and you were to take one of those little tiny ball pendulums and you were to hit it, it would go real fast, right? If you use the same force on like a clock pendulum, it's going to go slower, isn't it? And if you use the same force on one of those giant bells, it may not even move. In fact, you could probably run into it, it wouldn't move. Yeah. So the frequency goes real slow for those, right? It's the same relationship, by the way, if you look at like a xylophone or bell system or sound in general. Okay? For example, the fretting on a guitar. Yeah. How do you make the guitar go real high frequency? Real high pitch. Anybody know?
Tighten the string.
Yeah, you move your fretting down and it goes higher frequency, higher pitch. And so when like the guitar guy in your favorite music is going high frequency, high pitch, moves his hand real close in, right? Lower, further out, right? Okay. Okay. So let's look a little bit deeper in Hooke's law in IR spectroscopy. So according to Hooke's law, the spring vibrates at a particular frequency, and this right here is the frequency of that spring vibrating. That's going to depend on the masses of the two objects at the end. So mass 1 and mass 2. In this case, we would have the masses of atoms, right? So, and we would also have to take into account the spring's force, right? The force that's connecting the two things. That would be the normally stiffness of the spring, right? But in terms of bonds and atoms, that would be the bond strength, right? That would be the force that's associated with bond strength. And is it a single, double, triple bond, right? Okay. Okay. Does anybody have a question right here so far?
Is the constant, is that what, how they factor in the bond strength?
Yes. Yeah. So that's the stiffness of your spring normally.
Right.
In terms of atoms, it's going to be how strong the bond is, how close together it is, so how much it interferes. And also factor in double and triple bonds to a degree, because they'll have slightly different character. Yeah. When it comes down to actually doing this, you figure this out experimentally, and then you would work backwards, or you would calculate the force constants. Anyways, you guys probably aren't interested in that. By the way, an important little factoid here is that when you look at force constants and their effect on the world, they're always square roots. So almost every factor that affects the world, when you're looking at force constants, they're almost always square roots. Yeah. So this is something that PhDs in chemistry and physics always forgets this. Always forgets this. And then we'll talk about a paper, it doesn't change much. We got to square it. Got to square it. It's a damn square root, right? Yeah. Anyways, so right here we have the collapse down formula. This right here, which is this right here, is called the reduced mass. Okay? And note that it's the M1 times the M2 over the M1 plus the M2. Okay. All right, so the stretching mode for a vibration involving a highly polar bond, like a carbon-oxygen carbonyl or an oxygen-hydrogen stretch, is going to tend to have a very strong IR absorption. What sort of factor do you think plays into IR absorption? How strongly it absorbs? What pattern have you been noticing? The peak height would be the strength of the absorption, right? Anybody know what absorbs more infrared light? N2 or CO2? So if N2 absorbed infrared light really well, we wouldn't have to worry about global warming because it would already be maxed out. Because it's 70% of the atmosphere, right? So obviously that does not absorb very well, does it? No. Okay, how about O2? Does that absorb particularly well
No.
in the infrared? No, it can't absorb particularly well. And so what do you notice about both those compounds? What sort of dipole moment do they have? Sort of difference in electronegativities do they have? Yeah, they're nonpolar, right? They can't have a dipole moment because they're the same atom, right? Yeah. Okay, so CO2, different atom, right? Has oxygens with carbons, so it's a pretty strong absorber where it does absorb. Okay? How about H2O? How much of global warming do you think is actually caused by H2O?
Not much.
How much global warming do you think is caused by CO2?
More.
Okay, a little bit less than 1/3 of global warming is caused by CO2. 2/3 of it is caused by H2O. The vast majority of the global warming trend is caused by water. Okay, why don't we ever talk about water in the news?
What can we do without it?
Yeah, there's nothing we can do, right? So nobody ever talks about water because it's not controllable. Water goes the maximum amount it can for the temperature it can at that time. Okay, that's about it. And that's it. Like, you get low humidity days only because the humidity hasn't caught up yet, right? That's it. So, why is water a better absorber, by the way? What sort of band intensities would you be looking at?
Its polarity option is more electronegative than hydrogen or
Exactly, it has more polarity, so even the bands it absorbs at are more absorptive. Okay? There's also another factor when global warming. CO2 has less bands than water. So water actually covers more of the infrared spectrum. It's called the infrared window, actually, because it's the part of the infrared spectrum that's not well absorbed in yet. Okay? Anyways, so if we look at the stretching modes for vibrations involving nonpolar bonds, like carbon-carbon, these are going to tend to have weak or non-existent infrared absorption. And that's because they're very similar on both sides. And so if you got a symmetric stretch, nothing changing for this carbon-carbon, you actually won't see that in infrared. It has to change the dipole somehow. Okay? So for example, you could still get an infrared band with all the atoms being equal. You just need them to bend. Okay? If it bends, it's going to expose a dipole, isn't it? It's going to make a dipole. Okay? So the medium intensity infrared absorptions is going to happen if the two portions are connected by the bond are dissimilar and not super polar. Okay? Typically, the very high absorption stuff is typically going to involve oxygens when we're talking about organic chemistry. Okay? It sometimes is a halogen. Amines are rarer, right? Except for hydrogens, obviously, because everything beats hydrogen. Yeah. Okay, and so here we see some intensities. This is hept1-ene and hept3-ene. And so what do we see here? Well, we have this at the very end of the bonding, right? Okay. And what do you see about the differences on both sides of this? That's very asymmetrical, right? And so you have a lot of difference between your dipoles, don't you? Yeah. And so you can expose more dipole difference. This one right here on the middle, on the other hand, really kills the intensity of that, doesn't it? Because you start getting much more symmetric, don't you? It has the same stuff attached to both sides. And so it's very difficult to expose an asymmetric dipole. right? So let's talk some more about some important infrared stretches. When you first encounter an IR spectrum, an unknown molecule, don't just try to do the entire thing all at once. What do we learn about science? How should you always approach something that has more than like 3 things on it? Should you try to assign everything at once? Bam. No, you got to break it down, right? When we have complex problems, first thing we do is break them down, and then we build complexity from simplicity, right? Okay, and so even a simple compound can have dozens of peaks in its infrared spectrum. It's actually 3n minus 6, n being the number of atoms for a nonlinear molecule, okay? So even if we have, say, 5 atoms, we could have 15 minus 6, 9 bands that would be fundamental bands that you would have in that spectrum, right? And that's not including all of the overtones and combinations, which would be doublings of those bands, okay? So an infrared spectrum can look pretty complex if you just look at the whole thing, even for fairly simple molecules. So where do we begin? We're going to look at the peaks above 1400. This is outside the fingerprint region, and so you'll see the complexity drop off a lot. Most of the bands that will still show up there are going to be very low intensity. Okay? So you get a lot of this, the complexity disappearing if you look above 1400. Everybody see that? How we're looking above the 1400 again? And we lose a lot of that complexity, don't we? Okay. And so that's your first place to look. Now, many organic chemists, that's where they stop completely. And they think there's nothing complex about infrared spectroscopy. And there's no real, all it does is show you what functional groups there are. Yeah, if you don't look at half the spectra, yes. Yeah. I mean, yeah, sure. And yeah, so you oftentimes are going to hear things like if you ever start talking about infrared spectroscopy, oh, that's really easy. All you can identify as functional groups. You automatically know the person only ever looks up here. They've never looked down here at all. Yeah. That's where they stopped. Okay. Now, for your purposes, because we're going to combine this with other methodologies to determine what we have for a product, for the most part, that is about all you need from it. Okay? And then matching the fingerprint to something you already have looked up. All right? Okay, so right here again, we're going to look at the OHs here and see we have this very broad peak here, very strong peak, right? And that tells us we have an OH. Can everybody see it okay? Okay. We look over here and we have it shifted down with a bunch of stuff on top of it, right? Can everybody see those are different peaks? We have a very broad peak that's under all this, right here. And then we have other stuff on top. Everybody okay with that? Okay. And what that's telling us here is this is a very simplistic OH peak, okay? It would be a little higher if it was water. It'd be up here somewhere, right? Because again, that would be hydrogen, right? On both sides. And so this one is actually a fairly narrow OH peak. That's actually because it only has one hydrogen. Okay. But this one right here, very broad. This broadness actually tells us information. Did you know that? Okay. It actually tells us it's probably doing some sort of hydrogen bonding, and it's probably having things like dimers and stuff being made. And yeah, this would make dimers. They'd hydrogen bond to each other, so they matched. Right? That's actually what that's telling us, being so broad and shifting down like that. Okay, so this right here is that carbonyl OH, isn't it? Cool, huh? Okay, so the important part of all of what I just said, the first thing you need to be able to get out of that is OH is where? usually 3,600-ish, but we can be a bit lower depending, right? If we have something that can hydrogen bond, it's going to be lower. This can hydrogen bond, by the way, with itself, right? So if you have a bunch of molecules of this, they're going to hydrogen bond. Okay. This right here can actually form dimers, and so it's even lower. All right. But these are OH bands. Everybody okay with that so far? Okay, let's talk about that broadness of those OH peaks. So if you have a bunch of springs, right, and you just have them individually floating around, doing, it's going to have a nice, crisp, exact frequency, right? And so if you look at a xylophone, how do they have all the different pieces? Or bells. If you look at the bells or chimes, they always separate them, don't they? Okay? What happens if you don't have them separated? If you have them next, like, touching? Anybody know? Yeah, they're not going to have a nice crisp note, are you? You're going to have a combination, aren't you? Okay? And so what ends up happening is if you make hydrogen bonds between these hydrogens, these OHs, you're actually going to change all of their frequencies. And hydrogen bonds can be made in a variety of directions with a variety of forces on them, right? And so what ends up happening is what should have been a single perfect narrow peak, like if you had perfect resolution and everything was separated out by itself, there was nothing else going on, infrared peaks would look like lines. That's it. Okay? They never look like lines because you have other things happening to the molecule. And so what happens is the different energy states it's in, the different combinations of hydrogen bonds in this case, being the big one, is causing you to have different peaks under here. This is the majority of the molecules right there. Okay? Then over here is another energy state where less of the molecules exist. And so it's lower intensity, right? Over here is the same thing. You have another energy state, lower intensity. This might be the difference between hydrogen bonds being able like that and like that. Okay? Okay. Does anybody want one more thing to think about here?
Never.
No? Never? Okay. The other thing that you're seeing here for these broadnesses is rotations. So when you have molecules in space, they're always rotating. Okay? And so even if we had perfect gas phase, water molecules not interacting, you would actually see, and water molecules do this really well, they would actually have a bunch of individual bands like this. And those would actually be the rotations. That's the speed of the rotations. Yeah. All right, so this right here, again, you're seeing this fast exchange of these hydrogens, and so you're seeing this very broad mess that we sort of group up into one peak, right? We call that the OH band. Okay. For the carboxylic acid, what you'll notice here is, again, we have that same hydrogen bonding behavior, but it's not just going to be as simple as one hydrogen bond forming, is it? They're actually going to form into dimers. Okay? And so you get this double hydrogen bond forming, and you get these paired up like they're molecules with hydrogen bonds attaching. Okay? This is actually why when you're trying to predict for like carboxylic acids what the boiling point would be, you actually double the molecular weight because they always exist as dimers whenever you're looking at them. Okay, so let's go ahead and look a bit for impurities. So we think our structure is this right here. We're looking around, and what do you notice about this right here? Hey, that looks suspiciously like some sort of hydrogen-oxygen band, doesn't it? That's a dang OH stretch. Does that disprove this? No. When we're in nature, i.e. the world, what exists around us?
Everything.
I mean, kind of, but not always, right? Okay, so what's very famous in Tennessee? Why do all my papers stick together all the time and are floppy like this?
Water.
Water. Yeah, water's everywhere, right? And so water is a very common impurity, and this is what we're seeing right there. That's actually a water band. Okay? Specifically, it's the OH stretch from water. We can actually be alcohol too. I'm not exactly sure because it depends on what solvents they had for this. But water is very, very common. And alcohol, they could have just dried it a little bit by waiting. So, but I would hope it's not alcohol. Otherwise, they did such a half-assed job. All right. But anyways. By the way, can this hydrogen bond with itself? It cannot. It has a hydrogen bond acceptor, which is the oxygen, right? But it doesn't have the oxygen lone pairs. It does not have a hydrogen bond donor. Okay, let's talk about the NH stretch. So bands representing the NH stretches share many similarities with those of the OH stretches because, again, it's a fairly electronegative atom, again, with a hydrogen, right? So it's going to have similar frequencies. It's going to have similar, some degree of similarity in the heights. But those with the OH stretches are considered very generally easy to identify. They're going to be one of the first things you always notice because they're fairly strong and they're broad. They're extremely broad. The NH stretches are going to appear between 3,300 and 3,500 wave numbers. Your hydrogen bonding involving the NH bonds usually causes these bands to be rather broad, though not as typically broad as your OH stretches. So again, they're fairly broad compared to the other stuff, but see, that's nowhere near as broad as an OH, is it? You see that okay? Again, they're pretty strong, but not normally quite as strong as the OH. Okay? Like the OH is skinnier little brother or little sister, whichever one you want to think. Okay, and so what we notice here is, again, we have here NH2. What do you see about this right here? 2 peaks. Yeah. So unless they're symmetric completely, you're always going to end up with 2 peaks. Okay. Right here we see an NH, 1H, and we see 1 peak. Yeah. Right here we have no hydrogens on that nitrogen, and we get no peak. Yeah, no NH, right? And so that would be your tertiary amines right there, where we have the 3 carbons on that. So the NH stretching vibrations in your primary amines or amides. The 2 NH stretching bands are going to appear for the primary amine or the amide because, again, the NH2 group is going to have 2 different modes of vibration. This is going to be symmetric and asymmetric. Okay. Only in cases of extremely high symmetry, which you all will probably never see, could we get these bands disappearing. For my inorganic people, yeah, that's that character table. Yeah. Okay. So again, you have the symmetric stretch. Symmetric would be like this, right? Both coming in and out together. Asymmetric would be like this. They come at different intervals. Okay. And so you always end up with 2 of them. As long as you have some sort of dipole changes for these, they are going to show up. Okay. All right. This is your carbonyl stretching. So for each of the following compounds, your COO carbonyl stretch is typically going to appear in the corresponding range. This is an ester right here. It's 1730 to 1750 wave numbers. We have the aldehyde. It's going to be a bit lower at 1720 and 1740. Right here we have our ketone, and that's going to be at 1710, 1730. Notice again that's on the lower side than the aldehyde. Now, can you use this as absolute proof? I have it lower. It's at 1724. I have a what? Could I go, I have an aldehyde? I'm 100% sure.
No.
No.
You can say I have an aldehyde or ketone.
Yeah, I probably have an aldehyde or ketone. I have some confidence, but not a lot. Okay? And then you would want to look for other indicators, right? You could use other spectroscopies. You could use the fingerprint region. But you would need to have some sort of confirmation in some way. You could use the lack of a hydrogen for the ketone. So the aldehyde would have a hydrogen on the carbonyl, right? The ketone would not. Right here's the amide. That's 1630 to 1690. Notice it's quite shifted down because of that extra amine group right there. All right, so let's talk about conjugation. So when a CO group is conjugated with a CC or C triple bond, the frequency of the CO absorption is typically going to be lowered by 20 to 40 wave numbers. What did you notice about our carbonyl in the previous case of the example problem? It was lower than it should have been, right? Yeah. Why was that lower than it should have been? Was that attached next to something special? That was attached next to an aromatic ring, wasn't it? So it could conjugate with the aromatic ring, couldn't it? Okay? And so we actually saw a slight difference from that. And again, right here, we see an example of this. This one right here, 1721. And then when we get it in a place where it can be conjugated with this double bond here, notice it goes down by about 31 wave numbers, doesn't it? Okay. And that right there is your conjugation effect. All right. Anybody have any questions about that one? Okay. All right. And so right here we have the CC double bond stretch. And then we notice right here it's essentially absent, isn't it? It's been weakened so much we can no longer see it, right? Okay. Oh. By the way, this is water. See all the individual bands you can see? Yeah. Yeah. So for whatever reason, they had water in this spectrum. Yeah. All right. So, why is that peak disappearing, dang it? Exactly. You got it. So it's going to be that symmetry, right? So we're having that peak disappear because it has some degree of symmetry around it, right? We have carbon bonds on both sides, and so we end up missing some of the bands or they end up much, much lower in intensity because when they change, they don't change the dipole much, do they? Okay. All right. How about this one right here? Ooh, we got a nice aromatic ring, don't we? Okay. And so the aromatic rings right here are quite prominent, aren't they? Okay. What would happen if I changed the dimensions of that aromatic ring?
Shift the frequency.
Yeah, I'm going to shift a lot of that pulls, right? I'm going to shift this aromatic system, aren't I? It would be like trying to bend and stretch a wire, isn't it? It's going to change how the electricity flows through it. Okay? And so that's what I'm actually seeing right here is my magnetic field's changing because I'm changing that aromatic system, right? Okay. And it's very distinct sets of bands. You see these fairly high intensity sets of bands, and they're quite visible. Okay. And so aromatic systems are usually pretty easy to identify once you start knocking out that you have an aromatic system. So you usually look up here, CHs, I have a high CH. Then I look down here, I have this set of aromatic bands. Okay. All right, so let's talk a bit about the alkynes and nitriles. So the alkyne and nitrile bonds are both going to appear to be very sharp bands. They're going to be roughly the same positions. So the alkyne is going to be 2100 to 2260 wave numbers. And the nitrile is going to be between 2210 and 2260. It's not a lot of difference, is it? In fact, most times they're going to fall essentially in the same place. So typically how you distinguish between the two functional groups is you actually search for the alkyne CH peak. So if it's a terminal alkyne, we're going to have that terminal hydrogen, aren't we? And that's going to have a lot of S character, isn't it? Okay. And so you're going to see that all the way up at 3300. So that's a very nice piece of proof, evidence, that I have a terminal alkyne, isn't it? Okay. The presence of 1, so again, it's going to be a very sharp peak. It's going to be very consistent with your terminal alkyne. And so that's very good evidence of a terminal alkyne. The absence of 1 could still leave us with an alkyne because we could have an internal alkyne, right? Not at the end of the chain, within the chain. Okay? So the difference typically is going to be about the absorption intensities. So if we have a internal alkyne, one that has carbons on both sides, these are going to have very weak absorption intensities because they have carbons on both sides. The dipole moment doesn't change a lot when you stretch. If we have the nitrile, on the other hand, they're going to have moderate intensities because they have a fairly large electronegativity difference between the two. When you stretch it, you're going to see a higher intensity. Okay? Now, note that just because you have a strong band in this region, or a moderate band, I should say, in this region, does that automatically mean it's a nitrile? No, if it's the terminal alkyne, that's going to be fairly strong. Okay? Because it's at the end, right? So it doesn't have a carbon on one side. Okay? So it could actually be fairly intense. That's why you always want to check for that CH. Okay? So look at your band, check for the CH. CH isn't there. Medium, nitrile. Weak, internal alkyne. CH band is there. Terminal alkyne, right? Okay. All right, so let's look at some CH stretches again. So here we have the alkyne CH stretch. It's going to be about 3,300 wave numbers. It's going to be moderate intensity. The alkene CH, this is going to be 30,000 to 3,100, and it's extremely variable intensity depending on what you have around it. Okay. Aromatic is going to be CH. It's going to be 3,000 to 3,100. Again, this is going to be very variable in the intensity because you can pull electronegativity from it depending on what's around it. The alkane, this is going to be 2,800 to 3,000. Again, fairly variable in intensity, but usually you have some that are pretty strong. Okay. Again, depending on what's around it. The aldehyde, this will be 2 peaks. It's going to be 2720 and 2820. It's going to be moderate intensity, and this is pretty good evidence usually if you have a carbonyl and you're going, is that an aldehyde or is it a ketone? This is usually pretty good evidence. So you look for the CH, that's the aldehyde. Okay? It's fairly intense for what's normally in that area. There's not a lot of intense bands in that area. So, modern intensity, you'll see something like this. You guys see that okay? See the 2 bands? Okay. It's not uncommon to miss this band right here because of poor resolution, right? This has pretty bad resolution in this spectra. Do you know why I say it has bad resolution? Okay, you ever done your camera where you're focusing on the wrong spot? And then the slats, like you're trying to take a picture through a cage at the zoo, and then all the bars look like a solid object. You can just barely tell difference in intensities. Yeah, that's what you're seeing here, isn't it? And that's because it's fairly low resolution spectra. Okay? So they all look like they're merging together, but you can still kind of tell this is a separate peak, moderate-ish intensity, right? Okay. And that's the aldehydes right there. Anybody have any questions about those? These are some different examples of these different ones. Okay, make sure you practice and let me know if you have any issues with identifying these spectra. Really, it's going to be a practice thing. Okay, people get very good at this with some practice. All right, so some strategies for success: elucidating structure using infrared spectroscopy. The first thing you always want to do, where do you want to concentrate first? Do we do it below 1400 or above 1400? Above 1400. Why are we looking above 1400? Yeah, less stuff, right? Yeah, only a few things. They're all going to be major functional groups and hydrogens, right? Yeah. So, you can actually identify the major functional groups. Cool. Okay. Let's consider the functional groups that have more than one type of bond in step 1. And then we're going to look for the accompaniment to those types of bonds, right? If it's an aldehyde, it has to have a carbonyl hydrogen, doesn't it? If it's a terminal alkyne, it has to have a terminal hydrogen off the alkyne, doesn't it? Okay, a lot of these are hydrogens, but again, if we're looking at, say, a ester, or we're looking at a mid, we would have amines, right? We'd have amide nitrogen hydrogen bonds. We'd have a carbon nitrogen stretch, wouldn't we? Okay? And so you always want to look for the accompaniments to the type of functional group you think it is. If you don't have peaks that go with each of those functional group parts, you probably don't have that functional group, do you? Okay? And remember, you're building a case. You're looking for evidence. Right? Okay, so then you're going to look for the special characteristics of the absorption peaks that are identified in step 1. For example, the OH absorption is consistent of an alcohol or a carboxylic acid. The NH absorption, do you probably have an NH or NH2, i.e. one band or two bands, right? Okay, and you're going to subdivide that further down. Get more evidence to support having more specific structures, right? Okay. All right. You're going to establish whether a carbonyl bond is conjugated by looking at how far along the position is from where it normally would show up. Okay. If it's considerably shifted down than where you would have normally expected that type of carbonyl bond, then you know you probably have conjugation, don't you? Okay. And that gives you evidence for conjugation. All right. So right here we have an unknown. I am going to give you the chemical formula, but you don't know what sort of functional groups you have in this, do you? Okay. This is very typical sort of thing that you would have gotten from a MS, by the way, mass spectroscopy, right? You would have gotten possible formulas, and now is it an alcohol? Is it a ketone? Is it what? Right? How is this thing arranged? Okay. And so then you would go and try to figure out how this is arranged. So what sort of groups do we have here that gives us some sort of evidence for something? Okay. So what's one of the first things you want to go and look for? Does it have a double bond in it, right? You can actually eliminate that very easily by looking at your index of hydrogens, right? Okay. Okay. How saturated is it? Right? So how saturated should this be? So if you had 7 carbons, how many hydrogens should you have?
We should be like 16.
Yeah, so 7 times 2 plus 2, right? Okay. And so that would be 16. So we are how many short? 8 hydrogens short. 8 hydrogens short means how many sort of double bonds, rings, triple bonds, that sort of elements do we have? 4, right? Half of those. Okay. So we have 4 elements that would be things like rings, double bonds, triple bonds, that sort of thing, right? Okay. Okay, so we're going to look over here, and what do we notice first? Where do we look first? Above 1400. So we go up here. And what do we notice above 1400?
Somewhere around
3,300. This one right here. Okay, we got real strong, real broad, right? What does that tell us? That'd be down here. So what's a strong, broad peak up near 3,600-ish? Typically it's up a bit lower because it does something. Makes hydrogen bonds, right? Huh?
Alcohol.
Alcohol. Yeah, we have an oxygen, we have hydrogens, right? And so likely we have an alcohol, don't we? Okay. Okay. And so what else do we notice about this spectra? What do we notice up here? Yep, we have several sets of peaks, don't we? And so are the ones that we have here, are they all above, right between 3,000 and 2,900? We do have a set there, don't we? But do we have a second set? What about those? Right there. We have a second set, don't we? Okay. So we have the normal alkane hydrogens, right? And then we have not normal alkane hydrogens. Which ones are usually up towards like a 3050 or a 3100, that sort of thing? A little bit below 3100, right?
Alkenes?
Alkenes, is there any others? Not alkyne. And that'd be up here somewhere, right? We actually just did an example that showed this. That one was at 3101. Be an aromatic ring, wouldn't it? Okay. So right now our choices are alkenes and aromatic ring, right? Okay. Remember the aromatic rings were up in the 3,000 to 3,100-ish region. Okay. Okay, so we have alkenes and aromatic rings as possible options. We also need to have carbon-hydrogen bonds just on alkane, right? Okay. Okay, so what else do we have? What else sort of groups might we want to look at and comprehend? We have evidence here that we have like an alkene or we have some sort of aromatic group, right? What groups would come with that? Mm-hmm.
I was going to say near like the 1500 range, there's multiple peaks, which means aromatic, right?
Yeah. Yeah, that set of peaks a little bit over the 1500. That's another evidence for an aromatic, isn't it? The CC double bond would have just showed up here. Yeah. We do have something, but small. It's not moderate, is it? So we would have expected more from having... Remember, we have to somehow have 4 elements that will be triple bonds, double bonds, rings, right? Okay. Okay, and so we don't have a triple bond, do we? How do we know we don't have a triple bond? Yeah, there's nothing there, is there? Yeah. So we have to be all double bonds, don't we? We don't have a bunch of double bonds, do we? No. We have a set of vibrations that are all in that area where we would expect an aromatic, wouldn't we? Yeah. Okay, so we have some sort of ring. It's probably aromatic, right? And then we have an OH, and then we have some sort of alkane portion, right? Okay. So what sort of structure is this going to look like? So we probably have, what would the main portion look like? Is it a straight chain or a ring? Yeah, like a cyclohexane ring or a benzene ring, right? Which would be the aromatic. Okay. Off of that ring, what sort of groups do we have? Okay, very good. All right, and so that counts for 3 plus 1 for the ring, right? We have 4 of our IHD. That's the correct number of IHD, isn't it? Okay. Okay, so what's the last part? What do we have out of these options? These are all options that they kind of would be fit, right? Can we subdivide these options anymore based on what we've seen so far?
Maybe with like asymmetry versus symmetry.
Yeah, you're on the right track, exactly. I haven't taught you this part yet, but with what I've taught you so far, this is it. Okay? This is as far as you can go, and you would have to figure out some more evidence to try to determine which one this is. Okay? There's not really any way with how I've taught you so far to subdivide these. What we would actually have to do is we would have to look at the more of the fingerprint band region and the number of groups. Okay. Okay. So let's go ahead and try this with one more, because I want you to at least be able to get to this part and get these first steps done. Okay. Okay. So what would we be looking at for this? Okay, so again, you want to kind of start off with, do I have anything that's like a double bond, right? Just the formula can give you information, right? Okay, I'm going to have something that has an oxygen. I'm going to have something, does this have the correct number of hydrogens to be saturated? No. It's missing 2, and that's going to be a 1 IHD, right? I'm sorry, it's missing 4, it's 2 IHD. Yeah. And so, what do we have up here? What sort of groups do we have?
Like an alkane.
Yeah, these are the alkanes, right? And then we have one more pretty sizable hydrogen peak right there, right? And what would that correspond to?
Another alkene.
Yeah, alkene, right? We only have one, something like that, right? Okay, and so do we have any other features on this spectra here? Yeah, we have 2 very strong peaks, right? Okay. And so these 2 very strong peaks right here, what sort of groups would those correspond to? What does a carbonyl usually show up near? Yeah, so a carbonyl makes a lot of sense right here, doesn't it? And notice what we don't have up here. We don't have an alcohol, do we? No. So carbonyl makes a lot of sense here, doesn't it? Huh?
You do have a little in here.
Yeah, we definitely do. And some overtoning combinations, and yeah. Yeah, and a bad background, by the way. Yeah. But yeah, I find it funny. Your book could have gotten good spectra off of an IST
Yeah, but
and covalence, but
they didn't have time for that.
yeah. I guess not. Okay, folks, let me know next time. What do we have? In fact, I might throw this as the example problem. or something very similar.